Hey everyone, this is Connor Mead with the Calculation Center with another video in our Calculus series. In this one we'll be talking about the introduction to integration. Consider the graph of f of x, some function on the real line, denoted by this red curve, and fix 2 points a and b. We're going to talk about the area underneath the curve between these 2 points, so this shaded blue area here. And we're going to call that area the integral between a and b of f of x dx. Okay? Now, as a little side note here, this thing in here is called the integrand, this f of x dx. And the important thing to remember is that this x is actually what's called a dummy variable. We can call it whatever it wants. It really only exists within this integration. So it would just be precisely as valid to say this is the integral from a to b of f of u du, for example, or the integral between a and b of f of z dz or something. These are all fine and mean the same thing. So how do we find this quantity here, this area between the points a and b of f of x? As it turns out, we have this formula, that the integral between a and b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any function satisfying the equation df dx, d capital F dx I should say, is equal to little f of x. Okay? So any function that when you differentiate you get this function in here, you can use to evaluate this via this formula. You can evaluate this using the capital F's evaluated at the endpoints. Now, because when we differentiate capital F we get little f, we say f is an antiderivative of f. Okay? Furthermore, we sometimes don't put in these a's or b and call this the indefinite integral. And it's in this case we just kind of think of it as a machine that transforms this little f into this big F, where this big F is, we try to write it as the most general antiderivative of little f. But that's going to be a little more clear in practice than trying to lay out in technical terms. Okay, so now I'd just like to go over some important examples that we need to understand. So for example, when you want to know how monomials work, what's the integral of a monomial, and so you might guess by now that integration is kind of the opposite of differentiation. So when we integrate a function, we're really trying to find a function whose derivative is that thing we're integrating. So when we integrate x to the a, we're trying to come up with a function that when we differentiate it, we get x to the a. So if we remember our rules of differentiation, x to the a plus 1 divided by a plus 1 plus c is good as long as this thing isn't 0. Because when we differentiate this thing on the right-hand side of the equation, the c will vanish. C is just some arbitrary constant number. And we'll bring down the a plus 1 to cancel down here, and one of the ones up here will disappear because we have to decrease the power, and we'll be left with x to the a. Okay? This plus c is basically there to make it so that this is the most general antiderivative possible. No matter what value c takes on, this thing will always be an antiderivative of x to the a. And so here are some examples. X cubed, the integral of that is x to the 4 divided by 4, because when you differentiate it, you bring down the 4 out in front, cancels with the quarter, and you'll decrease the 4 to 3. And the c will go to 0. Similarly, x to the 20 is integrated to x to the 21 divided by 21 plus c, and the integral of x to the pi is equal to x to the pi plus 1 divided by pi plus 1 plus c. Now, notice that this formula is valid for a not equal to minus 1, so we better consider the case where a is equal to minus 1. Well, if we're talking about the integral of x to the minus 1 dx, we certainly can't use that formula. We need to come up with some function whose derivative is 1 over x. But we recall that the natural log has that function. In the first video we saw in the calculus section, we actually see this. That the derivative of the natural log of x is equal to 1 over x. And for technical reasons that we won't get into here, the integral between x, the integral of 1 over x, I should say, dx, is equal to the natural logs of the absolute value of x plus c. Now, you need this absolute value here in case you want to evaluate it at negative values. Sometimes you can omit it depending on the context, but just in general, it's safest to leave it there. Now, the other ones, we might also notice that there are many less clear-cut examples of simple integrals, because in general integration is much harder than differentiation, and there's some functions we won't be able to integrate. But there are some that we can pretty easily write down. For example, the integral of e to the x dx is e to the x plus c because once we differentiate this, this term will disappear again, and e to the x is its own derivative. Similarly, if we differentiate minus cosine of x, we get sine of x. If we differentiate sine of x, we get cos of x. Differentiate tan of x, we get 1 over cos squared of x. And these are all just exactly what you'd say, based on what we know from our differentiation tables. It should be noticed here, sorry, there's a minor mistake, this should have a minus sign out in front. Of course. It should be noted that like these things down here are often hard to spot because they don't look like they relate to trigonometric functions, so you really do have to know these. And more specifically, this one actually, this derivative of arctan seems to come up the most in problems in mathematics because it just kind of is a little easier to work in. So these are basically the important integrals that we need to go over. We'll talk about how we can use these results to get more complicated integrals solved in the next video. But until then, this has been Connor Mead with the Calculation Center.